Okay. Hello, good morning. Hopefully you can hear me. Sorry for the delayed lecture. I'm quite busy trying to juggle a lot of things. And for that reason, we'll study for just about 1 hour today. So I just wanted to let you know why we didn't start on time. So last week we were looking at digital to analog converters, and we'll complete them today and hopefully look at something else if time allows. Some of the dark specifications that we looked at, the main one really was resolution, which was the size of the step. So when you are converting a digital value, the size of the step from one digital value to the next one is what we called the resolution, or so to speak, the minimum change that can happen in the analog signal given a change in the digital signal at the input. Usually that digital signal change that produces a minimum change in the output, analog output, is usually the smallest change as well. Okay, so right. Yes, something that we didn't look at was actually the accuracy of the measurements. This is really similar to accuracy of any other measurement device like a meter. So if you've done instrumentation, this is not going to be very difficult for you. We can look at accuracy of the digital to analog converters in two ways. We can look at it in terms of the full scale error and also the linearity error. So those two, usually they are quite similar actually, or at least they give the same idea of accuracy or lack of, but these are just two ways that we can consider the accuracy. The full scale error is really the maximum deviation of the DAX output from its expected value, and this is usually expressed as a percentage of the full scale, whereas the linearity error is the maximum deviation in step size. Okay, so if the step size is supposed to be, say, 10 millivolts, and then you have an error of plus or minus 0.1%, it is usually that small difference in the step size. We know that for ideal values, the step size should be a certain, or the resolution, so to speak, should be a certain value. And so you keep adding those up until you reach the full scale. If that step size has an error, usually these are very small errors, that error will always be, as you go up in the staircase, you'll always create that error. And so by the time you reach the full scale, what you have is not quite similar to the ideal value of the full scale. If we look at this example, we have an 8-bit DAC that has a full scale output of 2 milliamps. Okay, so full scale is 2 milliamps, and a full scale error of plus or minus 0.5% full scale. And so what is the range of possible outputs for an input of that? This is really 2 to the power 8. 2 to the power 8 is 120. Is it 128? 2 to the power 6. I think this is, yeah. I think it is 128. So anyway, whatever that is, 2 to the power 8 is, yeah, 256. So 256, okay. So let's continue. Now we have, so basically we are expecting a full scale. Usually full scale is 2 to the power minus 1 of 255. Now the output is 2 milliamps. Full scale. First of all, we need to know the resolution. What is the resolution? Clearly, just one moment. The resolution is FS, which is the full scale, over 2 to the power n minus 1, which is, in this case, 2 milliamps over 255, which is 7.84 microamperes. Let me see. Right. So this is our resolution. So we can say that when our input is 0, our output is 0. The next time we go to 1, which is obviously 00001, 9 bits. These are 8 bits. We have, you know, 7.84. The next time we have now 1, 0, we are going to have 7.84 plus the resolution 7.84, all the way through. When we have everything 111, we should have 2 milliamps. So the question is, what is this is like halfway through the full scale, really. So if you have 1,000,000, the analog equivalent or the decimal of this is 2 to the power 7, which is 128. Now the question is, what is the range of possible output values? We can say that the ideal output is equal to 128 times the resolution, because the resolution is the step. So 128 steps times the resolution of 7.84, it gives us 1004 microamps. Unfortunately, here the question is saying that, let me remove this so that I can have where to write. The question here is saying that there is a plus or minus 0.5, sorry, percent of the full scale. We know then that the error is equal to plus or minus 0.5 over 100 times full scale, which is 2 milliamps, and that should be giving us plus or minus 10 microamperes. This is the size of the error, because we know that it is plus or minus 0.5% of the full scale. So that means that for our ideal result, which is 1004 microamperes, if the error is plus, we can add 10 microamperes. If it is minus, we can subtract 10 microamperes. And so the range becomes 1014 microamperes on the upper side, and on the lower side it is 994 microamperes. So that is the range of possible output values. The output value would be anywhere between 994 microamperes to 1014 microamperes. But the ideal value is 1004. It's just that you have a plus or minus, and that accuracy can go up or down. That's why it's plus or minus, which brings that kind of error. Any questions? Before we move on, please, if you have any question on this particular one. Okay. Now, we have another one called the offset error. Those of you who have done instrumentation, you know that there is usually an offset error in any meter. Basically, the question is, the offset error here would be that when you don't have, you are not measuring anything, or the input is 0, the output should also be 0. But usually it is a certain small finite value. It can be big, of course, but usually it is small, and we call that the offset error. It means that if I'm going to buy something like salt, and before they start putting the salt, the weighing scale already measures 0.5 kilograms. They are going to add 1 kg, it would read 1.5 kilograms. The problem is that they look at, you know, if they would look at 1 kg, meaning that they've actually given you 0.5 kg of salt. This is caused by the offset error. this is going to be caused by the offset error. I'll be back there in a moment in the chart. And so in this case, in this table, we see that we have our input codes. This represents 0, that represents 100, that represents 1,000, and so on. 800, sorry. And then that represents 1,500. If you notice, actually, this is the weight of the low significant bit. No. This is the LSB. That is the MSB weight. If you remember the weight, so you can work out why we have 1,500 here. Anyway, if we had an offset error of 2 millivolts, it means that instead of having these ideal outputs, each output will be having an additional offset error of 2 millivolts. And so we end up having 2,102,802,1502. This offset error can be removed. Usually these devices might have a small pin which you can change to control the offset meter. You know, like on a weighing scale, the weighing scales at home, there is a thing there that you can push on to control the offset error before you weigh yourself. Some of these may not have, okay, so usually what you do is you connect the meter or your analog, in this case, your digital analog converter, you connect some input and you know the ideal output, and then you can do some changes. Obviously, this offset error can also exist with accuracy issues or inaccuracy, you know, the other inaccuracy issues. And so we need to be careful to understand what we are dealing with. Are we dealing with the offset error? Are we dealing with some issues to deal with accuracy? Now, the accuracy issues obviously come from components that are old. They might be caused by temperature drift, maybe when the SiC heats up, you know, there's drift in the performance of the values of resistors and so on, and the other components within that. If I can go back to this one real quick, what I was saying here is that, okay, so we have 2 milliamps and we have found out that the resolution is 7.84, and we've been given an input data in fact, digital in of 10000000, which we know should be, based on this, should be giving us 128, which is that, times 7.84, which is which we got microamps, which we got as 1004 microamps. We've been given the error as plus or minus 0.5% full scale, where this is full scale. And so this is 0.5 plus or minus over 100, because it's a percentage, at 2 milliamps, which we found out to be plus or minus 10 microamps. So it means that this actual value or the ideal value may be off by plus 10 or minus 10. That's why I put it here in the middle. I could say that on the upper side, I can add plus 10 so that I have 1014 microamps. That is really the upper side. If we know what the accuracy is, that is the maximum possible output that this input can give us. Okay, including, clearly here we have included, we have catered for the maximum positive error. On the other side, on the lower side, it is minus 10, which gives us 994 microamps. So it means that our output, whatever it is, will range between these two values. But ideally, it will be 1004, which is bang in the middle. Okay. The settling time is another important DAC specification that really looks at the performance, the speed of the digital analog converter. It measures, it gives you an idea of the operating speed of the converter. And how you get the settling time is that you start from state where all the inputs are zeros, and you change them all at the same time to ones, and you see how quickly the output will settle down when everything has changed from all zeros to all ones. These are usually 10 small values, 10 100 nanoseconds, etc. These are usually, the cycling time is usually very small, but yes, it tells you, it gives you an idea of the measuring of the speed of the digital to analog converter. And we basically measure it by changing from all zeros to all ones, not going through the step-by-step increments as we have seen, but just changing from all zeros to all ones. And we see how long it takes the digital to analog converter to settle down, give you an analog output that is equivalent to the new state, which is all ones now. Finally, obviously there is a lot in the notes that you need to go and revise, but I'm going through the high level issues here for you. Finally, an important DAC specification is monotonicity. So when a signal is monotonic, it is moving in the same direction. It doesn't mean that it is linear, but it never changes direction. If it is increasing, it is increasing. So we can say a signal like this is monotonically increasing. If it is reducing, it is reducing. It never changes direction. So if you have a signal that moves like this and then changes and moves downwards, this signal is no longer monotonic, and so on. So you could say, for instance, that time is, or your age is monotonic, is a monotonic phenomena, because you're always growing. You never grow younger, you grow older. So we see here that when we are performing our digital to analog converter, we go through a staircase that is always increasing as we move from the start to full scale. Obviously, we know that after full scale, we come back down and go again, but we are looking at monotonicity only in terms of being able to move from the starting position all the way to full scale. How is that signal? If you notice in your DAC that sometimes you have a step that is higher than another one in future, then you know that there's a problem with your DAC, and we are going to see an example around that when we begin troubleshooting. But generally, that's what it means, that the performance of the DAC should always be monotonic as it moves towards full scale. Then we look at this integrated circuit. This part, I'm not interested so much in it, but you can look at it and try to understand it. But I'm interested in this integrated circuit digital to analog converter. As we said, some of these, usually these are available on chips or as packages, so you don't really need to construct one yourself. But an IC might look like this. You know, you have the power that runs it, obviously, and then we have our reference voltage, this one. This reference voltage, we already know what it means. It really measures, or it gives you the full scale value of your conversion. You have your input, so this is an 8-bit digital to analog converter. You have these two inputs. CS, we call it chip select, and you can see that it is active low, and write is also active low. And we see that we have a current output. So this one uses a current output, but out here, usually this is connected to ground, and you have out 1. Usually that's correct, and you have output 1. Output 1 is the equivalent current of the input, of the inputs, the digital inputs. So these digital inputs give out a certain current. If it's 0, 0, 0, 0 all the way, you might get a 0. 0, 0, 0 all the way, then the last one 1, the next step, you might get a certain value based on the resolution, etc, etc. Now this circuit is usually, you can add this one here if you want to get your output in voltages. So, you know, usually when you want to get your output in voltages, you add some op amp that we call a current to voltage converter. And that is the reason why DACs or digital analog converters with outputs that are current, with current outputs, are usually faster than DACs that have voltage outputs, because voltage outputs require an extra stage or that converts the current to the voltage. Okay, so that is an important point to note. Anyhow, we see that we need chip select, and we need read write, write, and we have inputs and outputs, right? Now, when this is 0 and 0, the inputs D7 to D1 will go to equivalent analog signal. So when these are both active low, it means the chip is selected and you can write, or what WR is like write. So you're pushing the information into the IC, and so you can get your output current or output voltage that is equivalent to that input. If any of these is, so for instance, let's say that this is 1 and that is X, or this is X and that is the one that is 1. As long as one of them moves from its active state, we know what that means. Usually what happens is that the information for this particular IC, the information D1, D7 to D0 is latched. By latched, it means that it enters into the IC, but it does not affect the output. So output unaffected. It will only be now, this information will be available, whatever this information is, will be latched inside here, but it will only change the output until both of these become 0. So that's why I've said X. Even if one is 0 but the other one is not, only latching can happen, but those inputs cannot be produced at the output in the analog equivalent format. However, eventually once we have like a 0 and that's a 0, then these ones will now give you an equivalent output on the analog side. That would be an analog output, sorry. Any questions? Okay. If there are no questions, let us look at some DAC applications. I mean, they are quite easy, most of them. The control, we can use the digital to analog converter to control systems. Usually we have, first of all, obviously measured the phenomenon that is analog, converted it to digital, and done some processing. And now we can convert the digital value into analog again, push it into an actuator like a heater, like a bell, whatever that actuator is, so that we can control the environment or perform some control based on whatever we are trying to do. Automatic testing, we can use an output from the computer to convert to analog, and this analog value could be used to test a certain system. You could, for instance, be wanting to test for errors or test for accuracies, and you can use that signal to do whatever you want in terms of testing. We can perform signal reconstruction because we are moving from digital to analog converter, but remember we started with analog. We used an analog to digital converter to create a digital signal. Now this is the digital signal that we put into the computer to process. After that, we need to convert this digital back to analog converter so that we have our analog signal. So you can see that this is the one that we use to reconstruct this digital signal back into analog. So this is really just the signal reconstruction application or process. Then the analog to digital conversion, usually analog to digital converters also contain a digital to analog converter. This is how it goes. It's that when you have some of them, not all of them, but usually some of them, when you are creating an analog to digital converter that we are going to look at later, usually part of the circuit you include a digital to analog converter. And then finally, you can use it for digital amplitude control. We know that if we have a system like this one, the output V out is equal to V reference times whatever your input is, binary data input, over 2 to the power n, which is the full scale. So, so you can see that if my V reference is 10, for instance, 10, that is like amplitude, I can get a V out. I can use this part of the equation to reduce V out. If I want V out to be equivalent to V reference, I'll make sure that this is equal to that, which means that everything here will be 1. I think this is -1 actually. You need to have a look at that equation. But if I wanted it to be half of V reference, if I need to get out about 5 volts, I can set my binary input to about 1000000, or whatever that is, or maybe 011, everything else 1, so that I'm roughly halfway through my counting rate, meaning that I'll have a half here, and that will multiply that so that my V out is around 5 volts. So you can see here that you have a binary number, and you can use this binary number to determine a scaling factor. This is the scaling factor that changes the amplitude, or the amplitude of this signal to a smaller signal. It does not change the shape, it only changes the amplitude, the size of, or the power of the signal. If you don't want to change the power, maybe you don't need to do this. But if you don't want to change the power, your scaling factor can be 1, where everything is all 1. However, if you cannot make the signal bigger, unfortunately, so this is not going to amplify the signal, but you can make it smaller, but by changing this scaling factor that multiplies it. Let us look at a small troubleshooting problem. So you have a signal, you have, this is the figure 11.3. You have a staircase waveform, but you have a problem. They are saying that C, input C to the DAC is open. We know that, and they've told us that this is a system that is TTL based. So we know that in TTL system, or TTL logic, when an input is open, it is interpreted as 1. It is interpreted as high. So that means that you have a problem. We want to see the staircase. We know that generally the staircase moves from, I'm going to say DC, BA, 0000, 0001, 0010, 0011, 0100, 0101, 0110, 0111. Then you start from 1000, 1001, 1010, 1011, 1100, 1101, 1110, 1111. Okay, so our output here ideally would be 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. And that's why you see here, you keep jumping from 0, 1, 2, 3, all the way to 15, because this is performing as expected. But now they've told you that actually C is always 1. C always high. C is always high, meaning that our output, actual output, is not 0 here, it is C. C is 1 here, so I can say 1. That means my actual output, instead of being 0, it will be 4. Here, C is 1, meaning 1 and a 1, I'll have a 5, and a 6, and a 7 here. Then we come here, we see, yeah. Then we come and we see that we have 0, 1, 0, 0. Just one moment. Have I reached there? 0, 0, 0, 1, 0, 0, 1, 0, 0, 0, 1, 1, 0, 1, 0, 0. Yeah, so we see that here, okay, so this is fine. And this will give us, when you have C as 1, we are going to get 4, because that is the weight of the third bit. And then we get 5 here because C is 1, 6. Obviously, in the table, if C is 1, that's okay because in that moment it is being interpreted correctly. It is when C would be 0 that we have a problem because since it's open, it will actually be permanently 1. We have 7. Then we have 1 and 0. But this 0, we are saying C is 1. So we have 1 and 1. 1 and 1, this is 8 plus 4, 12, I think. 13, right? 1, 1, 0, 0 is 2 to power 0, 1, 2, and 2 to power 3. 12, 11, 13, 1, 0, 1, 0 is 14, is it? Because that 1, 0, 1, 0 would be 1, 1, 1, 0. Because obviously C matches it's 0, but it's open, so it's a 1. And then we have 8 plus 4 plus 2, which is 14. And then this, I think, will be 15. Then we have 1, 1, 0, which is once again 12, 13, 14, 15. So if you draw this now, this staircase, instead of 0, you start at 4 and then go back to 4, you'll have something like this. You can see this black one is supposed to be the ideal one, and this is the actual one. You first start at 4, go to 7, then jump back to 4, 5, 6 to 7. At 7, you jump to 12, as we have seen in our table. From 7, you jump to 12. 13, 14, 15. Then you jump back to 12, as we saw in our table, back to 12 here. And then 13, 14, 15, which is there. So if your dark is performing in this way, first of all, we know there is a problem because the dark output should be monotonic. And yet you can see that sometimes we have reached 7, then we jump back down, we jump back down. This is not monotonicity. Secondly, if this is happening, then usually the first suspect you should get is that some inputs are open or some inputs are held permanently high. They don't change, they just remain high. And if I give you something like this, it should be very easy for you to see that actually, instead of having 0, this is the state for 0, 0, 0, 0. But because we have 4, we can look at the weight. What is the weight of the bit that is causing a 4? Since this is a 4-bit dark, we have D, C, B, A, and the weights of these are 8, 4, 2, 1. So here it's very easy for me to see that, oh, because instead of having 0, I have 4, which is the weight of C, it means that C is permanently high. It could be permanently high because it is always connected to VCC, or it could be permanently high because it is open. It's not connected anywhere. Yes, Amanya. I think Amanya asked is for the analog equivalence of C. Kindly elaborate about the 4. Yes, I have just explained this. That because instead of having a 0, we have a 4. We should look at the weights of these inputs. Imagine C and B were high permanently. I'm going to, let's just look at an example. If B and C were permanently high, if it is D, if it is C and B that are permanently high, it means that you would have D, C, B, A. This is 1, 1, 1, 1, 1, 1 already, 1, 1, 1, 1, 1, 1, 1, 1. So it is 0, 0, 0, 0, 0, 0, 0, 1, 0, 0, 1, 0, 0, 0, 1, 1. We can then continue here. 0, 1, 0, 0, 0, 1, 0, 1, 0, 1, 1, 0, 0, 1, 1, 1, right? Then usually that's another 0. Then usually we would have 1, 0, 0, 0, but this is not 0. This is, you know, these two are permanently high. So it's 1, 1, 0, 1, 0, 0, 1, and so on. Excuse me. Now this is what we see. Our output would then be this and that. This and that is 4 plus 2, 6, 7, 6, and 7. Now from 7 we go back to 6, and then 7, and 6, and 7. Then here we go to 8 plus 4 plus 2. So 8 plus 4 plus 2 is 14, 15. It means that the next one will be 14, 15, and so on. And so basically where we start is we start at 6, we got 7, we go back to 6, we got 7, we go back to 6, we got 7, we go back to 6, we go to 7. Then at this point, which is the 8th pulse, I think, or 9th, we jump to 14. We jump to 14, we go to 15, we go back to 14, we go to 15, we go back to 14, we go to 15, and so on. So you can see that depending on what is happening, you can create a table and create the staircase. And I'm going to bring this number. I always do. Okay. So yeah, so I give you a table, you can draw this quite easily. But it helps if you first draw the truth table. There's something I wanted to, there's something about data acquisition. So for instance, we usually have, we might have a signal like this, and before we get there, maybe before we get there, we can forget that. Let us look at analog to digital conversion. Analog to digital conversion, I'm going to take the next 20 minutes to explain this because I don't think it's just a little bit more complex than the digital to analog converter, but it is not as complicated as it might sound. So we should start with the control unit. The control unit is the part that controls the analog to digital conversion. This is ADC. And you can see it has a start command and a clock. The clock controls the conversion, and the start command obviously starts the conversion or stops the conversion. Usually it only starts the conversion. When the conversion has ended, we get a certain end of conversion signal, and usually it is usually high, and when we reach the end, it goes low. I just wanted to tell you this. We'll see how it works, but it is actually active NGT. When it goes low, it shows that the conversion has ended. If you want to restart, usually this start command will push it back to high. It will stay high until the conversion ends, at which point it goes low. Okay, so that is that. And now this usually you get a signal that is going into some form of register. This register, you know what a register is. A register contains digital bits. It can keep a word, so like a digital word, like a 4-bit word is kept within the register if it's a 4-bit register. And this information is moved into the digital to analog converter. Now remember that when you are converting an analog signal into a digital, you have an analog signal. That is your input analog signal. And this analog input signal is the VA. That is your input signal that you are going to convert. So we have information in here that we move into a digital to analog converter. This is the one that we've been looking at the last couple of lectures, how we convert from a digital to analog. The idea is that the information here is digital, obviously, registers keep digital information. That goes into the digital analog converter, which converts it into an analog signal VAX. This VAX is the analog equivalent of the information stored in the register. This goes in here, is compared with VA. And here we get either an analog, we get a high or a low. So the output here is binary. It is either 0 or 1. Now this is how it works. This comparator op-amp, if VA is greater than VAX, and if VA is less than VAX. If VAX is smaller, the input is 1, the output. This EOC is 1. And when VA is greater, this is quite confusing. Let me just rewrite it again. Yeah, I think I should start with VX. If VAX is less than VA, the output is 1. If VAX is greater than VA, the output is 0. So we know that when we have a 0, that is usually when we are going to end the conversion. So in other words, just to say it in a very simple language here, we can start, let's say that maybe our analog input is maybe, let's just say 10 volts. This is VA, is 10 volts. We usually, when we start conversion, we don't know what it is. So we start below, we start down. And we can say that our register has 0, 0, 0, 0. And this means that the VAX will be 0. And then we compare. So we convert this 0, 0, 0 into 0. We compare with VA. Obviously here VA is greater than VAX, so our output will be high. Then we shift this to, we change this to 0, 0, the next step. This will give us 1. VAX of 1 compared to VA will still give us a high. And we'll continue until 1, 0, 0, 1. What is 1, 0, 0, 1? That is 8, 9. This is 9. 9 compared to VA, which is 10, will still be a high. So we increase this one to 1, 0, 1, 0. 1, 0, 1, 0 is equal to 10. And when we look at 10 here, VAX of 10 compared to VA of 10, they are now equivalent. The op-amp will still give us a high. When they are equivalent, we are still going to get a high until the next step, which is 1, 0, 1, 1, which gives us now 11. 11 compared to 10, 10, 11 will give us a low, okay? And usually when we get a low, that shows that we have completed the conversion. Now, I should mention here, because this part might be quite confusing, I should mention here that VAX, for you to get to end conversion, VAX should be greater than VA by a certain threshold. That threshold is usually small, but basically we want to say that VA should be greater than VA. So VAX should be greater than VA plus VT. This VT can be very small. So maybe if VA is 10 volts, VT could be 0.5 volts or 0.5 millivolts or 10 millivolts. Whatever it is, at least when this tells us that when VAX and VA are equivalent, that is not enough to stop the conversion. We must continue until VAX is greater than VA by that threshold or more. Or more is fine, but at least by that threshold. And so we are going to look at an example to try to actualize this, what this means. But this is essentially what the conversion is, that we start from a very small digital number and we keep increasing it until we find a point where our digital input or our digital number is slightly greater than the analog input. And at that point, we are going to stop conversion. When we have a 0, stop conversion. And then we know that the value here, which is equivalent to VAX, which VAX is only slightly greater than VA, the number in this register is a good approximation of VA, but this is a digital value. So this digital signal is a good approximation of VA, and we just draw it out of the register and take it as our equivalent digital value output for the analog to digital conversion. So let us look at this example. This is actually something, this is a repetition. This is an ADC that is called the digital ramp. The digital ramp, you know, a ramp is like a staircase. So a ramp is usually moving from one level to another. And so that's what really staircases do. And so this is called a digital ramp, analog to digital converter. Others call it counter type, okay? Counter type converter. The reason why they call it a counter type analog to digital converter. The reason why they call it a counter type converter is because it uses a counter. Instead of a register, it uses a counter. We know that a counter is also a register. If a counter holds information, if you do not give it a clock signal, it will not change that information. So in a way, it's like a register. I mean, they are both made of flip-flops. It's just the difference in the application that makes one a register, the other one a counter. So based on the explanation that we had earlier, this counter will count from 0000. It will continue counting until its equivalent output VAX is comparable to VA and is slightly greater than VA by a certain threshold, as we have just talked about. Because the register, you might ask, where does the information keep coming from? But with the counter, it's obvious that if we give it the clock signal, it will continue to increase, to move. Now, this one is the end of conversion signal. The output of the ramp, we said that it is high until the end when it goes low. You can see that this EOC signal is active low here because it has a bar. And so it is because when it goes low, we end conversion. Okay, now that is also done. Let us look at this. This is our control circuit. Our control circuit has the start signal. Okay, this start signal, you can see this start signal is active low. So it should be low for you to be counting. If it is high, you cannot count. Now, usually you start by making it high. When we make it high, we reset. When start is high, reset counter. We can see that when this is high, the reset will reset the counter to 0000 or whatever number of inputs those are, because that is where we want to start. Also, when start is high, 1, reset counter, and 2, inhibit the clock. So you can see that when it is high, a high going in that bubble means that the output of that will deactivate the AND gate. That AND gate will always return a 0, basically, because you have a high going in, which goes through the bubble and becomes a 0, meaning you always have a 0 here. If you have a 0 here, it means that that clock signal will not go through. Now, for us to start, we push back the start button to 0. The moment we put this to 0, this becomes activated. And remember, initially this is high. And so you have a 1 going in here, a 0 here, meaning after the bubble it's a 1, and the clock signal now is able to go through. When the clock signal is 0, you have a 0. When it is 1, you have a 1, meaning that the clock now goes into that input. When it goes into the counter will start counting. It starts at 0000. The digital to analog converter converts this, finds that it's a 0. Compares VA and a 0 and probably finds that that's a 1, because VA is still, let's say VA is 4. VA is still greater than that. Now this one will count, you know, it will, when this 0 comes in here, the next clock signal will still go through because that's a 1. So that AND gate is still activated. We have a 0001. This converts it to a 1. Compared with 4, we still have a 1. A 1 goes through here. We get the next clock signal, which goes to 0010. That converts to 2. 2 is compared with 4. We still have a 1. A 1 goes through the AND gate, meaning that you have the clock signal coming in 0, 0, 1, 1. That converts to 3. 3 compared with 4, you still have a 1. That 1 still enables the clock signal to come through so that we can count now to 0, 1, 0, 0. 0, 1, 0, 0 will convert to 4. 4 is compared with 4, we still have a 1. We said that it should be greater than 4 by a certain threshold, whatever that threshold is. And we will go to 0, 1, 0, 1. This will convert to 5. 5 is compared to 4, and surely that is greater than the threshold. The 1 volt between them is greater than the threshold. We have a 0. The moment we have a 0 goes in here, it disables that circuit, meaning that you can no longer have the clock. And if you can't have the clock, you cannot count. So now the digital result that you take is the state of the counter, which at this point was 0, 1, 0, 1. So we can say that 1, 0, 0, 1, 0, 1 is what we are taking as the equivalent of 4 volts, which is obviously inaccurate here, but we can enhance the accuracy by obviously increasing the number of bits. If we increase the number of bits to a big number, we are going to have smaller resolutions that lead us to a much better output. So this is how the digital ramp works. And as you can see, it is quite easy. We have a counter that counts from down going up until we get a value that is greater than the input, the analog input, by a value that is at least equal to the threshold given or more. So it can be bigger, but it should be bigger by at least that threshold. Then we get our output. Let us look at this example. We have this digital ramp that we have just looked at. The clock frequency is 1 megahertz. VT, that VT is the threshold. The voltage threshold is 0.1 millivolts. The full scale is 10.23 volts, and we have 10-bit DAC. The analog to digital converter is really, it is the size of the DAC, so we can say 10 bits. It is the size of the DAC because you can see the only digital bit here is that and that. And so the question is, what is the digital equivalent obtained for VA is equal to 3.728? We need to first of all find the resolution. And in fact, the resolution is also here, but because it's like we start with the resolution, so to speak. The resolution here is that we know the resolution to be the full scale 10.23 over 2 to the power n minus 1, which is 10.23 over 1023. And I think this is 10 millivolts. That is 10 millivolts. So it means that we are going to start at 0. HP, the EOC on the previous slide seems to be inverted. I don't know what you mean by inverted, but I said that this inversion, EOC with a bar, if that's the inversion you mean, it just means that it is active low. As long as it's high, the normal process continues. This is an end of conversion signal. So it only ends the conversion when it goes low. And we can see that when it goes low, you have a 0 going in here, that this AND gate is disabled, so to speak. Yeah, okay, so let's go back here. So it means you start from 0, you keep adding 10 millivolts, the next step 10 millivolts until you reach this voltage. So we know that VAX should be greater than VA plus 10 than VT, sorry. The VT is 0.1 millivolt, right? So what is, and VA, we know VA is the input analog signal, which is 3.728 volt. So that means we need VA X to be greater than 3.728 volts plus 0.1 millivolt. Actually, this is 3.7281 volts. I'm going to create a new slide. Sorry, I'll get this better slide. So now, for us to get number of steps required, we are going to get the analog, the signal we want to obtain, which is 3.781. Is it 3.781? 72. Sorry. It is 3.7281, I believe, over the step size, because we want to get the number of steps. So what is the step size? Which is 10 millivolt, and that's a volt. And this will give us, this is 0.01, so 372.81 steps. But this, you know, so really this is 373 steps. That is, we can't have 372.8 steps. We have to go to the next one. But in this case, we must always go to the next higher one, not to the next lower one if it is closer. So even if I had got 372.15 steps, I must go to the next higher one, because remember, we must always meet the requirement that we are, our output digital equivalent is higher by a certain threshold. So if you go lower, you will actually abuse that requirement, and that will be wrong. So we always go to the next higher one. This is not the same as before in the last lecture when we were looking at how close we can get to a certain value, right? Because that was in DACs. This is in analog to digital converters. So what is the binary equivalent of 373? That is your answer. I think you know how to convert it. The digital equivalent of 373, because this is the info, this is going to be the one that is within the DAC. This is the one that will be in the counter here. And it is the one that they take as the output. So you usually get 373 and you convert it to binary, and I think you know how to do that. The conversion time, we have not yet looked at. Conversion time is how many clocks? How many clock signals do we actually get? It is going to be 373. These are the steps, because each step is equivalent to a clock signal, times, remember we said that our clock is 1 megahertz. So to get the time, we have 1 over frequency, which is 373. This is megahertz, 1 megahertz, 373 microseconds. And then finally, the resolution, we have found the resolution to be 10 millivolts. So that is it. I want to stop here with the analog to digital converter, the digital ramp, which I believe is quite easy. And the things that I'm talking about, these examples, this is where I'm going to set my questions from. So I can bring a question like this, obviously not exactly like this, but with a question that you can answer with this type of knowledge, type of approach. Thank you very much. See you soon. See you on Wednesday morning. Hopefully then we can have a complete lecture and finish the analog to digital converters and move to something else. I also gave out another assignment. I think it's due Monday after Maureen requested me to extend, because I think you're quite busy this week. So that's fine. I'm happy to do that, but please return them by Monday. There's a guy there's Omar Davis, I believe. He is the class rep for computer engineering. Once again, this information might be, if it's inaccurate, please forgive me. But he has no group. I've asked him to make a group with other people who have no groups. If there is no other people, if there are no other people with no groups or who have no groups, then he will have his own group alone, and I think that's really good. But if there are any people out there this week, make sure you get in touch with Ouma. Okay. Okay, so I'm just going to leave this slide here for just 1 minute, but I'm otherwise going to go off. The assignment that you are doing right now is individual. If I say individual assignment, I mean everyone works separately. So the one you are doing now is individual. The assignment you did previously was groups. I'm going to give some more group assignments. That's why I talked about groups once again. Okay.